All right, folks, without further ado, Mathijs. Thank you, sir.
Thank you, John. So my name is Mathijs Beckers. I'm from the Netherlands. I wrote 3 books. I run a YouTube channel, and there you can see my family, my wife and 2 sons, Huub and Luke. And I'm aspiring to become a nuclear communicator. I'm trying to explain people why we need nuclear energy. Here you see the Merrimack coal-fired power plant, which is just a couple of miles south from here. The American Rush coal-fired power plant. So here's the Sioux coal-fired power plant. It's just a few miles north from here. And this one is particularly interesting because this is the New Madrid coal-fired power plant, and you see an aluminum production facility right next to it. That's about 20 miles south, I believe it is. And this one is interesting too because this is the Granite City Works. It's owned by US Steel. On the right, you can see they have these tailings ponds, which they basically built into the river. There's a deep purple coming out on the north end, and there's light bluish coming out on the west end. And here's the Phillips 66 refinery, just a couple of miles north from here on Mississippi River. So my area of expertise, if I may call it that, is checking whether world-scale energy calculations are correct. That's the thing I try to do. And one of the biggest ones is Mark C. Jacobson's 100% renewable hypothesis. I'm going to show you one of the things that he did that isn't realistic. So this here is a model of energy production. In the late 2040s, Mark C. Jacobson expects 1.3 terawatt of capacity to generate a delta of 1.3 terawatt hours per hour, so that it can offset the loss of wind energy or solar energy. Well, the problem is you only have 85 gigawatts of hydro capacity in the US. So expanding it up to 1,300 gigawatts, well, that's going to be a problem, isn't it? So 2 papers have been written to refute this nonsense. I got the cue for the hydro argument from Clack et al. Because I missed it. When I first looked at the models, I didn't see it. I feel bad about it. Here are 2 very prominent YouTube channels called Real Engineering and Minute Physics. And they were asking the question whether we can power the world with batteries. The answer to the question is obviously no, because batteries don't generate electricity. That's the first thing to note. So basically they said, well, if we built 100 gigafactories, each putting out 100 gigawatt hours of battery storage each year, then we can power the world. Now, the point being here that eventually, if we do that over the course of 30 years, we will have enough battery storage, if we can make it that far, to store about 3,500 gigawatt hours of electricity. So that's not enough. That's certainly not enough to power the world. On the other hand, if you look at lithium production, if you want to create 10,000 gigawatt hours of batteries each year, you need about 259 tons per gigawatt hour of lithium. And we only produce about 36,000 tons of lithium per year over the entire world. So to get there, we need to produce 2.6 million tons of lithium just to get the production going. And that's not going to happen. We are not going to jump from 36,000 metric tons of lithium production up to 2.7 tons of lithium production. That simply isn't possible. So this is the thing where my heart gets beating, because I like to do world total energy calculations. And these are 8 different models. So the red ones you see on the right side, those are decarbonization models by Greenpeace, the World Wildlife Fund, and the Solutions Project by Mark C. Jacobson. And they assume that we can reduce energy demand globally, and they assume that we can electrify almost everything, and what cannot be electrified will be powered by hydrogen, for which we use excess energy. I still don't see it in the graph where the excess energy is coming from or how much it is, but seems to be there. So the lonely purple spike you see, that's the EIA prediction. And on the left-hand side, you see my status quo extrapolation. So I basically assume that the OECD and non-OECD are going to stay the same in per capita energy consumption. And then I extrapolated up to 9.5 billion inhabitants. I've written and read much uncertainty whether we can actually electrify everything, so that gives us conflicting assumptions because you simply don't know how much you can electrify. We can say, well, we can. There's multiple ways of electrifying stuff. However, can we ramp up production figures for these things, etc.? It's very uncertain. I'm not confident saying, well, we can electrify everything. I focus on copper because it's the lowest common denominator, which has the first biggest hurdle to take. So, for instance, renewable energy is about 5.5 metric tons per megawatt. Nuclear and gas and coal is about 1/5 of that. So it's still a ton per megawatt, but it's less. I want to find out how much copper we would need if we do a hypothetical 50-50 wind and solar energy mix. I create 3 models, basically one in which we would consume 150,000 terawatt hours of energy over the entire planet, up to 250,000 terawatt hours of energy per year. And you can see it ranges from about 50 to 81 terawatt of capacity, wind and solar. And I'm giving wind and solar a very optimistic 0.5 terawatt of capacity by now, because it's probably less at this moment. And I'm not provisioning for any backup of any kind. I'm just going to imagine as if this is a perfect solution with, the perfect energy grid, which will balance everything out, which is, of course, not possible, but it will make my modeling easier. So first, we are going to look, well, it's a little arithmetic, basically. So 5.5 tons per megawatt is the same as 5.5 million tons per terawatt. So 250,000 terawatt hours is 81.5 terawatts. And for 81.5 terawatts, if nothing happens in copper usage in renewables, so suppose the copper use efficiency, if you will, remains the same, we would need to extract about 454 million tons of copper, which is more than half of what we can economically recover right now. And I know that there's always this thing of supply and demand, so perhaps we can yank out that much copper within 30 years, who knows? But I'm very doubtful that we will. And by the way, all my figures in this regard come from the USGS mineral yearbook. So, and in the end, I boil it down to this: building everything we can from here until 2050. So we're going to be in deep trouble if this is the path we choose, which is the path people like C Jacobson like to put us onto. So here's my conclusion. I think that 100% renewable shouldn't even be a thing, not in science nor in politics. I question whether 100% renewable proponents have actually attempted to create such simple models, because, it's simple. If I can do it, any one of you can do it, because I'm not the smartest person in here. Then the final conclusion, how did this pass peer review? It still puzzles me up until today. So the peer reviewers must be knuckleheads. It's that simple. I'm almost finished. So here's my closing remark. I'm all in favor of using all utonium or allotonium or allotanium. So this basically means what are we going to use? I don't care. Thorium, uranium, depleted uranium, weapons-grade plutonium, whatever. We need practical technological achievements from you. So we really need to get cracking on it. That's it. Thank you for